Benzene is very stable because of its aromatic structure. However, a strong electrophile can break into a benzene ring in a reaction called an electrophilic aromatic substitution reaction. The mechanisms that we'll be dealing with in this chapter are all essentially the same. Benzene attacks a very strong electrophile, which adds to the benzene ring. This breaks the aromatic structure, and then a base abstracts a proton to reform the aromatic structure. Alkenes react with electrophiles in an addition reaction. However, because benzene has an aromatic structure, that structure is more stable, and so we get a substitution reaction when benzene reacts with electrophiles. Adding substituents to benzene requires a very strong electrophile. And we're going to learn about 7 different electrophiles that we can use to add substituents to benzene. The first 3 of those is adding a halogen to benzene. Adding bromine or chlorine to benzene uses essentially the same reagents. For bromine, we mix iron in with bromine to make iron 3 bromide. This reacts with bromine to form a very strong electrophile. So bromine Br2 by itself is not a very strong electrophile, but now we have a very strong electrophile, and so benzene can react with this electrophile to add bromine to the ring. After this, a base abstracts the proton, and then we have bromobenzene. Chlorine reacts in the same way, except instead of iron 3 bromide, we use iron 3 chloride, and that makes a similar super electrophile. Iodine will also add to a benzene ring. However, instead of using a similar reaction, iodine can actually be oxidized. We're not going to show a mechanism for this, but it can be oxidized to I+, and this can add to a benzene ring in a similar mechanism. We can also add a nitro group to benzene. To do this, you need to add concentrated nitric and sulfuric acid to benzene. And sulfuric acid is a stronger acid than nitric acid, and so it actually protonates nitric acid. This protonated nitric acid can then lose water to make a nitronium ion. The nitronium ion is the electrophile that we need. So benzene can react with the nitronium ion to form the intermediate, and water or some base can abstract a proton to form nitrobenzene. Sulfonation of benzene occurs with a similar reaction, but instead of protonating nitric acid, sulfuric acid can self-protonate. So concentrated sulfuric acid will protonate itself and lose water to form a sulfonium ion. The sulfonium ion is the electrophile that we need, and so benzene can attack this electrophile and lose a proton to form benzene sulfonic acid. There are 2 more electrophiles that we're going to learn about. Those both add carbon to a benzene ring. We have Friedel-Crafts acylation and then Friedel-Crafts alkylation. The acylation reaction starts with either an acyl chloride or an acid anhydride. We're going to show this with an acyl chloride. So if we add aluminum chloride to an acyl chloride, it will lose the chloride to form an acylium ion. This acylium ion is the electrophile that we need, and benzene reacts with this electrophile to add an acyl group to the benzene ring. A base will abstract a proton to form an acylated benzene ring. The alkylation reaction occurs similarly where aluminum chloride pulls the chlorine off to form a carbocation. This carbocation is attacked by the benzene ring to form the intermediate. A base pulls off the proton to form an alkylated benzene ring. This reaction has some limitations, however, because as you learned last semester, carbocations can undergo hydride and alkyl shifts. So if you're wanting to add a propyl group to a benzene ring, you actually get rearrangement of the propyl carbocation to form a secondary carbocation, which is more stable. So you get a hydride shift, and the product that you were seeking is not the product that you get. So this is just a caution that we need to be aware of for Friedel-Crafts alkylation.